Hello everyone. I'm here today to talk about our work called Variance Reduced Smooth Functional Reinforced Policy Gradient Algorithms. It's joint work with Professor Shalabh Bhatnagar and I'm Deepak Ramachandra. Now imagine you're trying to teach a robot how to walk or play a complex game like chess or Dota 2. It's pretty much a trial and error task. It's all about how to make the most of an experience to get better and better. You can imagine a graph like so. For every strategy represented by a 2D plane for simplicity, we get a total reward uh, on average. For chess, it's like win probability. To find the best strategy, uh, it's essentially an optimization problem. There is a surface we don't see, but starting from a random point, we want to reach to the top. But well, it's really hard, and we'll just settle for a nearby local maximum. A classic approach is just gradient following. Think of it as a blind man trying to feel his way uphill to a peak. He sort of never knows how high he has reached, but as soon as he reaches a place where everything nearby is lower, he stops. Under certain conditions, uh, this technique is known to work well. So there is this policy gradient theorem from Sutton and his colleagues from 1999, which states that the gradient of the cost function is given by this weighted sum involving the state visitation distribution, the action value function, and the gradient of the policy with respect to its parameters. Essentially, if you compute this and then change the parameters theta in this direction, eventually you'll reach the local maximum. The reinforced algorithms from Williams back in 1992, as shown in the classic textbook from Sutton and Bartow, is as follows. Pretty much uses Gn for Q, and the updates made over a period of time will just add to the factor of the distribution of states and then make this log gradient of the log probability into just the gradient of the policy. Um, but the problem here is that although the gradient is unbiased by definition, it has too much variance to be useful in practice. That variance problem has led to some widely used and powerful algorithms. A to C, advantage actor critic, uses a value function as a baseline. This baseline helps give a stable estimate of how much better an action is than an average action at that state. It also uses generalized advantage estimation that sort of balances the bias and variance trade off. On the other hand, proximal policy optimization uses a clipped surrogate objective to prevent the new policy from straying too far from the old one in a single update, ensuring stable learning. These are great algorithms, but we need more data to fit the value function apart from the policy gradient. We aim to develop a simple algorithm that handles high dimensional problems effectively, utilizing less data and achieving superior online learning capabilities. Our work is inspired by two papers, Evolution Strategies and Augmented Random Search. ES showed that using a simple simultaneous perturbation stochastic approximation gradient estimator could be viable and a scalable alternative to the traditional policy gradient methods. ARS extends this idea by normalizing the state vectors and, more crucially, using only the top performing perturbations while estimating the gradient, and it uh, promises good results on the Mujoko tasks. We combine these ideas and we show that a simple two simulation SPSA gradient, when combined with variance reducing techniques, can be even more sample efficient and competitive. So let's try to understand exactly what is the function that we're trying to maximize. So we have the policy parameters, um, and when we play out the game according to the policy, we there is it's not very deterministic. There is randomness due to the policy, and then there is randomness in the environment, which combine, and at the end we end up with a total reward. So mm, there is no explicit gradient here, except that what is provided from the policy gradient theorem. Uh, so at the end, we have this black box function, total reward. So what is this SPSA, simultaneous perturbation stochastic approximation really? For this, you just consider a functional, uh, call it grad hat, that takes in a C1 function as the first argument and a d-dimensional point as the second. So the task of this is to um, estimate grad j. So what it does is it samples a random perturbation in d dimensions from the standard um, Gaussian distribution, and it computes this quantity. It pings the uh, a j function twice and gets this quantity. And if you think about it, this is pretty much the scalar dot product of the gradient along this random direction delta as c tends to 0. Um, and then this scale, it is a scalar multiplication with the random direction itself. Uh, so it's sort of a vector. The output is a vector, and the magnitude is it's proportional to the um, dot product of the gradient with this direction. In practice, we don't really have access to J. All we have is this noisy function, let's say call it H. It's like if you have this policy with parameters theta and you play the game and you find a reward at the end. So if you play the game with the same parameters policy, you could get a different reward. And to model that, we are just using this eta noise. And then um, essentially expectation over this noise variable, we retrieve the on average cost function, cost of the reward function. An interesting result from professor's paper from 2013 says that we can essentially use grad h, grad hat h, to get an estimate for grad j at theta. So where is all of this headed to anyway? Uh, So the expectation of grad at uh, h mm, under the random variables eta and delta, of course, is quite close, very close to grad j at theta within an additive term of order c, when c tends to 0 anyway, so it's quite small. So the proof, or the sketch rather, is is as follows. So we have grad at h, and then was the definition, and then from the definition of h we just get this. um, from here you can just imagine like the Taylor's expansion, and then this expectation goes to 0 because everything is independent, um, and then we use the fact that the individual components delta I are independent of each other and then have 0 mean and unit variance. So at the end you end up with this theorem. So why is this whole process, why is this called a smoothed functional? Why the name? Well, the functional part is easy because grad hat takes the function h as an argument. It's a function of a function. The smooth part is a bit nuanced. It's just that we're approximating the gradient of the expected performance, um, grad j, by the convolution of h with a multivariate normal density. So the idea of this uh, grad hat into the expectation, the integral with probability distribution over delta, um, the whole mathematical form is pretty much a convolution. And if you think about it in image processing, a convolution with a Gaussian kernel results in a smoothed image. So that's where the nomenclature comes from. So here I've uh, plotted the same J as from before. Um, and what I do is start from a random point, and the algorithm has access to not J but H instead, and it uses that to calculate grad hat H. Uh, and it uses that to move the parameters, and eventually it reaches a local maximum. Uh, the path is a bit shaky, but eventually it sort of gets there. So at this point, I want to compare our previous algorithm with ARS. Apart from normalizing states, the update from ARS uses n vectors instead of one vector from the multivariate Gaussian. So at the end, whatever grad hat you calculate over n samples and average it. This is to reduce variance, of course, but this would come at the cost of additional measurements from H. Um, and then in the improved version of ARS, they use only the top k directions sorted based on the magnitude of this scalar. And empirically, it is known to provide a higher improvement. Now, back to our algorithm, smoothed functional reinforce, SFR. The key idea is to perform the same update with just two measurements of H instead of the 2n. This allows us to utilize our experience with the environment more efficiently by continuously updating the policy. To address variance, we adopt standard techniques such as sign gradients and their clipped versions, both norm-wise and component-wise. The main contribution of our work is a detailed proof of convergence for both the SFR algorithm and evolution strategies. This result automatically extends to ARS, thereby providing a strong theoretical foundation for all the algorithms we discuss. We then move on to an empirical comparison between ARS and SFR. The central question here is, given a fixed interaction budget, the environment, is it better to allocate more interactions per update for stability but fewer updates overall, or to just use 2 episodes per update but perform proportionally more updates? For completeness, we also include comparisons with PPO, TRPO, A to C, and the vanilla reinforce. Our evaluation spans both a simple grid world environment and the more complex Mujoko suite. Now we look at a simple grid world setup. The agent has to move from the top left to the bottom right in an n cross n grid. The environment is made simple on purpose. The closer you are to the final state, the greater the reward. However, to make the process more random, when the agent tries to move in a direction, there is a 10% chance that it's pushed in a particular perpendicular direction, resulting in uncertainty in the total reward. Also, we limit the total number of actions in an episode, so we don't end up with an infinite loop. We use a small 4 cross 4, then a 10 cross 10, and a large 50 cross 50 world with 2500 states. Um, so we can see that SFR outperforms everything else. So from the table, we see that uh, it gets the highest reward across every grid and has the least variance too. And then it achieves a high performance with fewer episodes. Next, we evaluate on the Mujoko benchmark tasks introduced by Todorov et al. In 2012. We test on 4 standard Mujoko environments: Swimmer, Hopper, Half Cheetah, and Walker 2D, covering a range of state and action dimensions from small to relatively high. Each action lies in -1 to 1. We test 5 algorithms on 4 tasks. Each experiment is run with 3 random seeds, and we also sweep over different hyperparameters. To keep things fair, we limit all algorithms to make at most 1 million interactions. Our method, SFR2, achieves the highest reward on swimmer and half cheetah. On Hopper and Walker 2D, it's competitive with the best results while still outperforming common baselines like PPO, A2C, and TRPO. All in all, SFR delivers strong results across tasks, even under the same interaction budget. This was just a quick summary of our work. For the full details on the convergence proof, experimental setup, and results, please check out our paper. The link is in the description. We would also like to thank the anonymous reviewers at TMLR whose feedback helped us strengthen this work. If you have any questions, feel free to drop them in the comments. And thanks for listening.